Hi everyone. So behind every electric generator on the planet is Faraday's law of induction. And basically Faraday realized, and then others went on to improve the techniques, but Faraday realized that what we have is an ability to convert motion into electric potential. And that is basically what's behind any kind of engine or generator. Basically, we're converting one kind of energy, kinetic energy, into electric energy. And so that is the conversion that's behind every electric generator. And this is the picture you might want to think about in your mind. Basically, you've got a ring, okay, conductive ring inside a magnetic field, and you spin the ring. Okay? Now, you got to spin it in the right way. You don't want to spin it like this. That doesn't change anything. The geometry is exactly the same. You don't want to spin it this way, but you want to spin it across the magnetic field. And by spinning it across the magnetic field like that, you generate an electromotive force inside the ring, because essentially when the ring is in the orientation that it's pictured right here, there is no magnetic flux, because the magnetic field is exactly parallel to the area contained inside that ring. And so there's no lines of flux actually penetrating, going through. Therefore, there's no flux. But when we flip this ring so that it's perpendicular, parallel to the ground here in this picture, then we have full magnetic flux going through. It's the magnetic field multiplied by the cross-sectional area of that ring. And so as that ring spins around, it's going from 0 to plus, 0 to minus, 0 to plus, 0 to minus, 0 to plus. And that change in magnetic flux induces the electric potential inside the ring, which is going to push and move charge, create current. Now, because of the way the ring spins like that, there's essentially a sine wave associated with that, because it's going up, down, up, down, up, down, up, down, the magnetic flux. The magnetic flux starts at 0 in this picture, goes to a maximum, goes back to 0, goes to a negative, goes to 0, etc., and cycles, right? And so that circular cycle is what drives the circular cycle of electromotive force. And that's what this picture here represents. Basically, the electric generator creates a voltage that goes up, down, up, down, up, down, up, down. This is called alternating current, as opposed to the direct current we get from a battery, which is just a straight push. You know, here we've got a jostle back and forth, back and forth, back and forth. And it was not clear initially that this was useful at all. You know, it sounds like basically you've got a net effect of 0. It's just like a water wave carries no net momentum, therefore there's no force. But just like a water wave can be used to transmit energy, an alternating current can also be used to transmit energy. And it took a while for engineers and physicists to figure out how to harness this. But that's what powers every single electric circuit inside your house. That's the source, the electric source from the power plants are all alternating current. And so in order to really get anything to work, every plug or every electric component's got some sort of thing inside of it that transfers, moves the alternating current into a direct current that our devices have a tendency to use. These AC to DC converters can be quite complex, but they are essential to pretty much everything we're using. So just a little bit of nomenclature on alternating current before we really dive into that. That will be the next lecture, in which we talk a lot about how AC electronics work. But one thing I want to introduce right here is that if we have an alternating voltage here, there are two voltages that are of interest. There's the peak voltage, which is the maximum. It's the amplitude of that wave. That peak voltage is characteristic of the magnetic field, the cross-sectional area, all those things, right, through Faraday's law. However, because the power that's experienced through the effect of this alternating current and alternating voltage oscillates, really it's not so much the peak that's experienced, but something called this root mean squared, the RMS voltage. And the RMS voltage is connected to the peak voltage through this kind of equation. Now this square root 1/2, the square root 1/2 is what's true for a sine wave. If we have a different shaped envelope, like a triangle wave, a square wave, we have a different number. This number is kind of representing an average, a net impact voltage, if you will. And those are the voltages that we measure with voltmeters and things like that. It's the RMS voltage, and that's why it's important for us to understand this subtle distinction in nomenclature.